I promised an example when the uniqueness of the decomposition into a product of irreducibles fails. Here is the example. We will have R is z of root of -5. And this is example 4 from the book. In this ring R, we have six is an element of this ring, is equal to 2 times 3, both are elements of this ring, and another decomposition is 1 plus root of -5 times 1 minus root of -5. We need now check that these are indeed two decompositions which into products of irreducibles that are substantially different. That means that we want to check 2 and 3 and 1 plus minus root of -5 are all irreducibles, and 2 is not an associate to 1 plus or 1 minus root of -5. 3 is also not an associate of these two. So we will check that these are indeed two substantially different decompositions. Of fix into product of irreducibles. Let me recall what we'll use for this to check all that. We have theorem 1019. Let me recall that this as a set is s plus t root of -5. S and t are integers, and we consider all that as a subring of the ring of the field of complex numbers. We have theorem 1019, which tells us that in general in z of root of d, d is a square free integer, n of a is 0 if and only if a is 0, and secondly we have the multiplicativity of norm, n of a times n of b. I recall, that's recall, the norm itself is defined as norm of s plus t root of negative 5, any element from this integral domain is s squared plus 5t squared. I also recall theorem 1020, which will help us to distinguish units and therefore irreducible and therefore associates. U, an element of any such ring, is a unit if and only if its norm is either plus is equal to, either plus or minus 1. I want to start with a technical proposition which will help us. There is no element in this ring with norm 2 or 3. So this ring, root of negative 5, the integral domain, has no elements A such that norm of A is 2 or norm of A is 3. This is example 3 in the book, where this is discussed. The proof is very simple. We simply recall what the norm is. So what norm of any element s plus t root of negative 5 is s squared plus 5t squared, and this is either bigger or equal than 5 if t is not 0. Indeed, this is 5 times at least 1, square is positive, plus something else, so at least 5, and that may be, if t is 0, then this is s squared. S squared may be 1, maybe 4, or maybe bigger equal than 9 if t is 0. 2 and 3 are missing. So t is not 0, the norm is 5 or bigger, t is 0, 1, 4, 9, and so further. The only value smaller than 2 and 3 is 1. After that, immediately 4, 9, further. That's it. We proved this simple proposition. And now I want to check that these two decompositions of 6 are substantially different. Well, first of all, I want to check that these are indeed decompositions into products of irreducible. So first of all, I want to check that 2, 3, and 1 plus or minus root of 5 all in this ring, root of negative 5, are irreducibles. Indeed, here is the proof. Let us check that 2 is irreducible. So let 2 be a product of 2 elements of the ring, A and B. I will now use the multiplicativity of norm and take norms. Norm of 2 should be equal norm of A times norm of B. Norm of 2, I recall norm is written here as squared plus 5t squared for 2. S is 2, t is 0. The norm is s squared, which is 4. So 4 equals norm of A times norm of B. So, yeah, by the way, I should probably mention that these norms in this ring, because D negative 5, this D, is negative, all norms are non-negative. It is a sum of 2 non-negative numbers. So 4 is a product of 2 non-negative integers. All norms are integers. The options are 2 times 2 and 1 plus 1 times 4. Nothing else. So either these two integers, norm of A and norm of B, are 2 and 2, or 1 and 4. I write in parentheses because I don't want to write 4 combinations A, B, B, A. That makes no sense. One of them is 2, another one is 2. One of them is 1, another one is 4. And there is no other options. But this option is ruled out. Cannot happen. As 2 is not a norm. We proved that there is no integer, there is no element of norm 2. Of no element. There is no such element. This is just that's the only option. So one of these factors, either A or B, has norm 1. One of the factors A or B has norm 1. And we know the characterization of units. Everyone who has norm 1 is a unit. This is if and only if. So if norm is 1, then U is a unit. Thus a unit. So in any factorization of 2 into a product of two factors, one of them must be a unit, which means 2 is irreducible. Same story with 3, with only small changes. Instead of 4 here, I will have 9. Instead of 2, 2, I will have 3, 3 decomposition of 9, which cannot happen because there are no elements of norm 3, as there are no elements of norm 2, and another possible decomposition of 9 is 1, 9, so one of the norms is 9, one of the factors must be unit. 3 is also irreducible. So similarly with 3, also irreducible. It is very similar with 1 plus minus root of 5. Let us still see that 1 plus root of 5 or minus does not matter, be decomposed into two factors a and b, and I again do the same thing. Norm of 1 plus or minus does not matter. Root of 5 is norm of a times norm of b. S squared plus 5t squared. S and t are 1 plus 1, 1 or 1 negative 1. Anyway, squared, they do not matter. 1 plus 5 times 1 is 6. And we are again in the same situation. These two norms are either 2 and 3 in any order, or 1 and 6. And that cannot happen because there are no elements. No elements of norm 2 or 3. So neither this nor that does not exist, or neither this nor that exists. And in this decomposition, one of the elements has norm 1, one of the factors as norm 1. Therefore, a unit, and we conclude that thus 1 plus or minus root of 5 are both irreducibles. So, one more thing to check is maybe this is still the same decomposition. Maybe 2 is an associate of one of them and 3 is an associate of another one. Let us check that this is also not the case. So let me write it as a separate proposition. 2 and 3 are associates to neither one plus root of negative 5 nor 1 minus root of negative 5. That is because if two elements are associates, so if A and B are associates, by definition, A equals BU and U is a unit. We can take norms in this identity, so norm of A must be equal to, and norm is multiplicative, so we take a product. But U is a unit. We know all units have norms plus or minus 1. In this case, all norms are non-negative. All norms are non-negative. Therefore, negative 1 is ruled out. Norm of U must be 1. Norm of a unit must be 1. So that is, for two associate elements in this integral domain, norms of associates must coincide. So if two elements of the ring are associates, then their norms must be equal. The converse is not true. These two, 1 plus and 1 minus root of negative 5, have equal norms but are not associates. That is just a marginal remark. So now we calculate the norms of all our elements. norm of 2 is s squared plus 5t squared, t is 0, so this is 4. And norm of 3 is 9, while norm of 1 plus or minus root of negative 5 is 1 squared, 5 t squared, t is 1 or negative 1, doesn't matter when it is squared, it is anyway 6. So we see that 2 is not associated to either of them. The norms are different. 3 is not associated to either of them. The norms are different. 4 is not equal to 6. 9 is not equal to 6. So 2 and 3 are irreducibles, which either of them is not associated to any of these irreducibles. What we have checked this way, that these are indeed two different decompositions. Let me show it again. Two different decompositions of an element 6 in the ring into products of irreducibles 2, 3, two irreducibles. This is an irreducible, this is an irreducible. 2 is not associated to either of them. 3 is not associated to either of them. All different. This way, we got it. We got a definite failure of the fundamental theorem of arithmetic with two substantially different decompositions, not up to units, not permutations, nothing helps. These two decompositions are different. Now, what is the matter with these different decompositions? Why that happens? What's wrong with this ring? This is for the first time we see an example when the factorization is not unique. Why? So, in a sense, that may be explained as follows. So, what? About what? The reason for the existence of different decompositions. Factorizations. There are two different factorizations. Factorizations. So, although two, as we have checked in this integral domain, is irreducible, the principal ideal 2 is not prime. Sometimes they distinguish between primes and irreducibles. You remember we called integers primes, polynomials irreducibles. Difference as the distinction may be made as is the principal ideal prime or irreducible. Up to this point, that was not a distinction because things coincided. And that was one of the reasons we were able to prove the uniqueness clause in the fundamental theorem. Now, these turn out to be two different things. The element is irreducible, but the ideal is not prime. Typically, ideal up to this point, in this class, all have seen ideals, principal ideas generated by irreducible elements were primes. We did not emphasize on that, but now we see the distinction. The ideal is not prime while the element is not irreducible. Let me justify this claim. The justification comes from two propositions. First, I want to prove that these elements, 1 plus minus root of negative 5, do not belong to the, one proposition is going to be enough, do not belong to the principal ideal 2. At the same time, their product while their product 1 plus root of negative 5 times 1 minus root of negative 5 is 6, which is an element of ideal. So that is clear that the product is 6. 6 is an element of ideal. Why? I want to prove that this claim, but do not. That these two are not in the ideal. Their product is. That exactly tells us that the ideal is not prime. Product of two elements out of ideal turn out to be inside the ideal is not prime. Why these two elements are not in the ideal? Now let us, for the proof, write what the ideal generated by 2 is. This is as a set. 2 times any element of the ring. S and T are integers. So what we need to prove that to check for no integers S and T, one plus or minus root of 5 equals an element of ideal 2s plus 2t root of 5. Root of negative, sorry, all 5's are, of course, negative 5's. Negative 5. Oh yes, this is obvious that these two cannot be equal. So if two complex numbers are equal means separately their real and imaginary part are equals. 2s as an even integer, 1 is odd, they cannot be equal, and same, by the way, here plus minus 1 and 2t also cannot be equal. So indeed I justified that 2 is not ideal. 2 does not, ideal generated by 2, the principal ideal generated by 2 does not contain 1 plus or minus root of negative 5. Same actually is true about, or same is true about the principal ideals three. It's very similar. 2 and these ideals 1 plus root of negative 5 and 1 minus root of negative 5. All these elements are irreducible. All these ideals are not prime. These ideals are not prime. Well, it is not interesting to check for 3. It is immediate as for 2. Same argument will work. Let me check it for 1 plus root of negative 5. So a similar proposition will be 1, 2 is not in the ideal 1 plus root of negative 5. 3 is not in the ideal 1 plus root of negative 5, while 2 times 3, 6 is, in this ideal, is an element of the ideal 1 plus root of negative 5. So that looks a little bit less trivial, and let us check that. So that will imply immediately, so this ideal is not prime. For the proof, first of all, okay, let me start with this statement. It was obvious that 6 belongs to this ideal because it's a multiple of 2. It is also obvious that 6 belongs to this ideal because we multiply that by 1 minus root of negative 5, some element of the ring, and get 6. So as 6 is a multiple of 2, 6 is a multiple of this element, therefore we have to multiply by 1 minus root of negative 5, therefore 6 is inside this ideal. So that is obvious. Now let us check that 2 is not an element of this ideal. Yeah, I want to check 2 is not an element of this ideal. Thus, I want to check that 2 is not equal to 1 plus root of negative 5 times c for any c an element of this ring. In order to check that, it suffices to check that the norm of 2 is not equal to norm of this element times any norm of any element from this ring. So I want to say that because norm of 2 is not equal norm of 1 plus root of negative 5 times norm of c for any c. You may, of course, write c as s plus t root of negative 5 and try to follow same lines as we followed here. I just want to do something a little bit differently and possibly slightly more elegant. Norm of 2 is 4. So what is written here, that 4 is not equal to 6. This is the norm of this element. 1 squared plus 5 times 1 squared. 5 plus 1 is 6. Times norm of c. Yes, indeed. Because indeed true, because norm of c is an integer. Positive integer does not matter, integer for any c an element of our ring. And 2/3 is not an integer. We're done. So I supported the claim that all these ideals 2, 3, 1 plus and 1 minus root of negative 5, all these principal ideals are not prime ideals. And now that allows for an idea to fix the fundamental theorem of arithmetic so that the theorem becomes true. Now, the fundamental theorem of arithmetic may be fixed, or can be fixed, in a way such that the corrected version is true in this integral domain. So first of all, I put a question mark here. I want to say that on a diagram, or at the end of previous section, there was a question mark, which is now filled. We have an example where the decomposition exists, but is not unique. Now we want to fix that situation. We think about the product. The factorization for an element of our integral domain as this factorization P1, P2 into a product of irreducibles as a factorization of ideal A into a product of ideals. P1, P2, Pn. And we know we previously looked at factorization into a product of irreducibles. Now I want to drop the condition that all ideals are principal ideals. Instead, I would impose the condition that all ideals are prime ideals. Principal and impose a condition that all ideals are prime ideals. At this moment, I want to recall that was the idea of Kumar or Dedekind. The very word of ideal comes from ideal number. So that was the original way, more than 100 years ago, to think about ideals which are possibly not principal. They look like this, but this number may not exist. This is an ideal number. Now we have a general definition due to those people who thought originally about principal ideal generated by an ideal number. They coined the definition of ideal. And now we look at this decomposition. It may happen that our irreducibles do not generate prime ideals. These ideals are not prime ideals. Continue decomposing. Maybe this ideal, which is a principal one, becomes a product of two prime ideals, or several prime ideals, and so further. After that, the question becomes whether a decomposition of an ideal, again, not necessarily principal one, into a product of prime ideals exists, and more importantly, is unique. Definition of product of ideals is as follows. Let I and j be ideals and R. R is still an integral domain, and set Ij to be as a set A1 B1 plus A2 B2 plus up to AN BN for some n bigger or equal than 1, where all a's belong to the ideal I and all b's belong to the ideal k belong to the ideal j. Elements of I, elements of j. We take products, element of I, element of j, and take finite sums of these products. This is a set one has to check, and this is easy. To check that Ig defined this way is an ideal. So if I and j are ideals, then so is Ij. Ij is an ideal. Also, if I and j are principal ideals, then this multiplication simply reduces to multiplication of generators. So this is indeed a generalization of usual multiplication. So if these all ideals were primes, then we do produce this decomposition and stop here. Nothing new happens. Something new happens if the elements are irreducible while the ideals are not prime. So in the case when we already have the fundamental theorem for irreducible elements as representation as a product of irreducible elements, we change nothing. So if I is X and J is Y principal ideals, then so is a principal ideal IJ XY. That is also an easy to check statement. You can do it on your own. So now, if you have decomposed some element or just some ideal into a product of ideals, you have to decompose further until all elements, all ideals are now prime ideals. If it was a decomposition of an element into a factorization into a product of irreducibles, these ideals, as we have seen in the example, may not be prime ideals. Decompose them further, factor them further into a product of prime ideals. The fundamental theorem of arithmetic will now state the corrected version of the conclusion of the fundamental theorem of arithmetic would be every ideal can be written as a product of prime ideals in a unique up to permutations. We don't need SSAs anymore. Up to a permutation of permutations of factors of the a permutation of their factors. way. I skipped the condition of the theorem. There should be a generalization of ACC, but we don't need, we now do not, will not be happy with ACC on principal ideals. We have to reformulate that somehow to cover the new situation. So we need something for the existence of the factorization in the integral domain. So it is not in every integral domain because the existence may fail, as we know. Let me, I will not, I will skip that. I will not tell you the correct condition for the theorem, but after all, in the correct situation, the condition is a little bit technical, and the technicalities go a little bit beyond the scope of this class. But the idea is, in a good situation, reasonable situation, we do have the uniqueness saved in this way. And let me, instead of going into these technicalities, the book wants to tell you something about integers in algebraic number fields. I don't think you will benefit from that a lot, so skip that. That is only one example. There are others. Let us skip it altogether. You will not appreciate that example. Instead, let us finish well with our example. So back to the example. With the quadratic ring z of root of negative 5. In this example, there are three ideals, three prime ideals. So the three ideals, this is example 5 in the book. The three ideals which are already not principal ideals, Q1 with just two generators, 3 and 1 plus root of negative 5. Q2, 3 and 1 minus root of negative 5. And P, this is 2 and 1 plus root of negative 5. And this is the same ideal as 2 and 1 minus root of negative 5. So these have just two generators. So as a set, any integer times 3 plus any integer, or any element of the ring plus times 3 plus any element of this ring times 1 plus root of negative 5. So factors, multipliers are elements of the ring, of course, not just integers. And with these three ideals, the three ideals are prime, all prime ideals, and the unique decomposition or factorization becomes six, neither 2 times 3 nor 1 plus times 1 minus root of negative 5, but p squared q1 q2. Now this ideal, it is a principal ideal, we started with this number, this element. Now we look not into the factorization of this element, but into the factorization of the principal ideal generated by this element. Here is the factorization, unique factorization into a product of ideal into a product of prime ideals. Where are our two different factorizations? Here they are. The p squared is the p times p. This is the ideal p. If you take all products and sum them together according to the definition of product of ideals, you do it with p times p. What you produce this way is the ideal 2, principal ideal. So p times q1 is the principal ideal 1 plus root of negative 5. P times q2 is the principal ideal 1 minus root of negative 5. And finally, q1, q2 is 3. So when you write it 6 as 2 times 3, that's true for ideals, but these ideals are not primes. What you write is p squared q1 q2. This is the ideal 2. Oh, sorry. Here I don't want to put parentheses. Let me put just distance between them. So this is I put parentheses for principal ideal. So this is p squared, which is 2, times q1 q2, which is 3. Or you may write a same product as pq1 pq2, and in this case that is going to be the ideal 1 plus I put two pairs of parentheses to emphasize this is an element, this is ideal generated by this element. 1 minus root of negative 5. These are our two different decompositions. Principal ideals are not prime ideals. We have two different decompositions. These are permutations of decompositions into four factors, PP, Q1, Q2, corresponding to these decompositions into principal ideals. These ideals are already P, Q1, Q2 are already prime ideals, and this decomposition is unique up to permutations which we see. This is, I hope this gives you a clear idea how it should work, why the word ideal came into the existence in the connection with these rings. I did not prove many statements which I made here, and you may look at the exercises uh, 14 till 20 devoted to in the book, exercises to this chapter, this section devoted to this this example. I don't know, maybe if there are difficulties, I will have to show you how to solve these exercises. Hopefully, you will be able to do it on your own. All statements are not difficult. Every time you do a routine checkup according to definitions. So nothing goes beyond, nothing conceptually goes beyond what we discussed, what I tried to explain. That is probably the end of story, what we have covered this semester. And I hope you enjoyed the lectures. Thank you for listening. Thank you very much.